the discoveries of the James Webb Space Telescope have subverted the case for the huge explosion. The James Webb Space Telescope has quite recently conveyed an undeniably exhilarating revelation that is sending shock waves through the world of physical science. Through a single stunning picture, it has annihilated well-established discussions, leaving researchers shocked. The period of hypothesis is over, as Webb's most recent catch is both outwardly charming and a distinct advantage that vows to alter our view of the real world. What red-hot discussion among researchers has this picture conclusively finished? In what ways is the shocking picture caught by the James Webb Space Telescope rethinking our comprehension of the universe? Join us as we see the reason why it's getting terrible, as Webb's finding closes the discussion in material science with a breaking blow. The principal issue with astronomy is that researchers can't come to an understanding about how old the universe is or how fast it is growing. This unanswered peculiarity has baffled researchers across ages, and they are leading different research to find answers. Cosmology is the field of exploration that spotlights on understanding how the universe was made, how things are assembled, and how it has changed over time, and ultimately, will end. This field has seen critical advancement in the past 100 years. The currently accepted cosmology model, the theory of the universe's origin, proposes that the universe has been extending from an exceptionally hot and thick starting state for around 13.8 billion years. This extension is measured by the Hubble constant, which demonstrates the speed at which the universe is extending. However, estimations of the Hubble constant are not direct. Measuring the Hubble constant can be broadly classified into two gatherings: local estimations and early universe estimations. Local estimations involve the investigation of the galactic collections of the universe. For instance, Cepheid variable stars and Type Ia supernovae act as standard candles to quantify the Hubble constant. Because of their splendor, astronomers can gauge how the universe's extension influences the rates of these objects to conclude their distances and, therefore, work out the Hubble constant. The second group is the estimation of the early universe. Researchers use observations of the cosmic microwave background radiation, CMB, the glimmer of the Big Bang found in the 1960s. The CMB showed the microwave radiation of the early universe when it was only 380,000 years old. By measuring the small temperature and polarization swells emanating from the CMB, cosmologists can lay out the age of the universe and its pace of extension. However, here's the issue: the aftereffects of these two techniques don't relate. The outcome seen through local estimations affirms that the universe is extending quicker than what we gauge in light of CMB information. Due to these distinctions, researchers have been endeavoring to uncover the explanation behind the outcomes. As such, further research is being led to learn more about the secrets of the universe. As things stand, the distinction in estimations shows that there is either new science we have barely any insight into or botches in one or both ways by which we are measuring things. Thanks to the James Webb Space Telescope, we can see into the dark universe clearer than at any other time before. The telescope can show the slightest and most far-off components, planets, and cosmic systems we wouldn't have thought it was feasible to see due to its capacities. Researchers normally expected that data from the JWST would help us in definitively computing the Hubble constant. However, the principal wave of data has strikingly made matters more muddled. They have given us new experiences that are not cognizant with what we assumed we knew. Might this information at any point lead to another hypothesis and alter how we contemplate space? Assuming this is the case, we could have to survey how we interpret how the universe works. For example, we may find particles and powers that have never been noticed, or it could mean that dark energy, an unexplored world factor answerable for the speeding up extension of our universe, should be reconsidered. Up until this point, the manners in which we think about space have developed as we proceed to find new things. For instance, in 1965, when scientists found the cosmic microwave background radiation, it filled in serious areas of strength for the thought of the theory of how things came to be. Before then, researchers believed that the universe was everlasting and was continually extending at a uniform rate. However, the new proof demonstrated that was not true. Additionally, when we found out towards the end of the 1990s that the universe was ceaselessly growing, we discovered dark energy and its impact on the universe's development. Accordingly, every time we learn something new, we question whether it fits into our ongoing frame of work. If not, we come up with new ways to deal with comprehend the universe better. To this end, the issue we are facing in cosmology today could prompt the disclosure of the most awesome answer for the universe. While the problem is challenging, it is also thrilling, as it forces us to foster more mechanically progressed instruments to investigate space. This cosmological situation likewise joins the logical community from various nations, as each researcher wants to find out about the universe. Above all, it shows that science is continually changing and developing as we more deeply study space. Alongside the Hubble strain, there is likewise a concern known as the SH strain. This is as to the spatial circulation of issue in the universe. This can be utilized to draw a foundational image of the universe and perceive how it has developed. The space experts refer to this peculiarity as knottiness, since there are areas of room that have bunches of worlds closely assembled while other regions are scanty. Specialists additionally utilize the cosmic microwave background, CMB, and glimmer from the beginning of the Big Bang. This light has been in movement for roughly 13.8 billion years, bearing news from the early universe. Through the CMB examination, physicists can interpret how the universe was knotted in its introduction to the world, which ought to match the observational knottiness of the universe right now on a huge scale. But here's the trick: these results additionally don't adjust with the CMB's knottiness. The non-circular gravity appropriation model suggests that the matter circulation at the early phase of the universe was more homogeneous compared to the one noticed utilizing gravitational lensing. As such, we can figure that there is something different that we are not considering in the clarification. This takes us back to the idea of dark matter. What precisely is dark matter, and how can it work? The truth is, this has yet to be addressed. However, all hope is not lost, as the James Webb Space Telescope, JWST, is set to reclassify the field of space science with its extraordinary high resolution and camera awareness. The telescope will look at early times of the universe and examine the primary universes and stars formed. This makes it conceivable to get more accurate estimations of infinite development and matter dissemination. These basic inquiries will require exact observation and perhaps new approaches from a hypothetical point of view to figure them out. Whether the end is seeing more significance to dark energy, finding totally new physics, or acquiring a superior comprehension of dark matter, the implications will be far-reaching. Handling the secrets of the universe resembles figuring out a zillion-piece puzzle blindfolded. Researchers should be seen as careful investigators who are focused on and fixated on tackling these mysteries. The most recent endeavor, called Project Flamingo, is proof of NASA's increasing enthusiasm for scientific exploration. Utilizing one of the world's most highly acclaimed supercomputers, stationed at Durham University in England, Project Flamingo is a monumental achievement in the realm of computational innovation. It costs more than 50 million hours of computer time and features 30,000 cores and counting. The project highlights the academic community's intent to explore the universe thoroughly, significantly focusing on dark matter. Dark matter, the mysterious substance that neither emits, absorbs, nor reflects light, is inferred to exist due to its gravitational effects on visible matter. Its elusive nature continues to fascinate researchers. However, Project Flamingo's approach is different from previous simulations. It incorporates all possible types of cosmic elements, from galaxies with the most diverse gas content to stars and black holes at the center of the universe. Through this organized method, the consistent evolution of the universe was modeled from an initial rough sketch. The motivation behind ambitious undertakings like Project Flamingo is clear: to explain cosmic discrepancies where the calculations seem incorrect and don't fit into the universe's structure. This difference in measurements suggests a fundamental misunderstanding in our current grasp of the universe's workings. If these measurements were compared to musical genres, they would be like jazz and classical, each with its own method but still related. Flamingo attempts to unify these different perspectives and sharpen our individual perception of the universe. However, despite its complexity, cosmic tension persists. This tension continues to serve as humbling evidence that we still have much to uncover about the universe. The universe appears reluctant to trade its secrets with us so easily. With each new data point and simulation model we add, like Flamingo, an increasingly vast new universe opens up, with new problems to solve. It's a never-ending mission where each answer leads to more questions, revealing entirely new layers of understanding. This shows that the nature of our quest to unravel the universe's mysteries is complex and ever-changing. Since Edwin Hubble made his groundbreaking discovery of the expanding universe in the early 20th century, the pace of our understanding has been astonishingly fast. Past scientists have consistently made numerous discoveries about the universe's dimensions, like the Big Bang Theory, dark matter, and dark energy. They have explored the universe by examining the cosmic microwave background, CMB, and meticulously recording the positions and velocities of galaxies with an ever greater level of precision. Each of these achievements is like obtaining another crucial piece of the cosmic puzzle. This has driven us to strive for greater comprehension of the universe. Undoubtedly, the universe is shrouded in mystery, and it can be risky to reveal its realities too soon. At every scientific step, researchers present refined theories, updated models, and more, redefining the boundaries of our knowledge. For example, the Big Bang Theory was once highly controversial but is now considered a fundamental part of scientific knowledge. Similarly, dark matter is no longer a theoretical idea but a tangible cornerstone of our cosmic puzzle. The discovery of dark energy, an unknown force driving the universe's expansion, was a late 20th century revelation, and it has become a key piece of understanding the universe. Let us now examine the different ways scientists have attempted to solve the puzzle of the universe's expansion over time. They have worked hard, yet some pieces still haven't fallen into place. Long ago, it was widely accepted that every object in the sky, from the sun to the stars and planets, revolved around the Earth. This geocentric view was challenged by Copernicus and Galileo, who asserted that the Earth and other planets revolved around the Sun, ushering in a revolutionary perspective. Fast forward to the 20th century, when Einstein revealed a new revolutionary perspective about the physical world. He proposed a model where space and time are not separate entities but a four-dimensional structure called spacetime, in which they are intertwined. His findings gave the universe a dynamic nature. In the 1920s, Hubble's observations revealed that galaxies were moving away from each other, indicating that the universe was expanding. With this fact, scientists developed the Big Bang Theory, which suggests that the universe originated from a singularity and has been expanding ever since. Initially, it was believed that gravity would eventually halt the inflationary cycle. However, astrophysicists discovered something in the 1990s that turned out to be astonishing. Not only is the universe expanding, but its expansion is also accelerating. This surprising result led astronomers to develop the theory of dark energy, a mysterious repulsive force that pushes components of the universe apart. The Flamingo project emerged as a crucial player in this field, offering more than a typical supercomputer simulation. It presented an immersive virtual reality model of the universe, using data from both the cosmic microwave background, CMB, and galaxy observations to construct a detailed digital representation of the universe. The primary goal was to assess whether, given our current understanding of physics, the early universe could naturally evolve into the complex structure observed today. A notable feature of Flamingo is that it considers both dark and ordinary matter in the simulated universe, unlike previous models that tend to ignore ordinary matter. This fully developed approach can be compared to how one learns about a car's functionality by considering its chassis, engine, seats, and wheels. However, when it comes to reconciling the clumpiness observed in the CMB with that in the local universe, some challenges still remain. Flamingo missed the mark. Inconsistencies persisted between the universe's development rate and the conveyance of matter, leaving cosmologists grasping for explanations. Differences continue to exist between the cosmic development rate and the distribution of matter, prompting cosmologists to seek out alternative models. Some anticipate that new physics and laws that go beyond our current understanding must be developed to explain the inconsistencies. Others suggest that our measurements or understanding of dark energy could be flawed. Such strain is a classic example of mystery, with the universe itself serving as the central puzzle. To sort everything out, the capabilities of the latest telescopes and advanced modeling have barely begun to solve the riddle. We are now at the edge of the cosmic cliff, where the unknown is hidden. However, the endless search for knowledge is one of the joys of science. Each question opens another path in the ongoing quest, with each trial and simulation pushing us closer to understanding cosmic secrets. The James Webb Space Telescope, with its advanced capabilities, has provided us with exceptionally sharp images and data, which add layers of complexity to existing tensions in cosmology. It reveals galaxies that appear more scattered than what our current theories had predicted. Despite persistent efforts, including elaborate simulations like the Flamingo project, which aim to integrate both standard and dark matter effects, a mismatch remains. Flamingo aimed to reconcile our theoretical models with observational data, yet the universe has proven to be more resistant than expected. So, where do we stand now? Our models of the universe are undergoing significant challenges, potentially signaling a paradigm shift where our theoretical foundations may need to be reviewed. These challenges are not setbacks but rather signs pointing us toward a deeper understanding. Every discovery builds upon another, prompting scientists to refine their ideas or theories. Each new tension or discrepancy hints that science and our comprehension of the universe must be corrected. The workings of the universe fluctuate like no other, with the details being influenced by some mysterious force from the nature of physics. Despite the complexities involved, there is a persistent desire to explore and understand what we have, which keeps us on the path of discovering new mysteries about the universe. To reach the edges of the seemingly endless universe, where understanding becomes blurred and uncertain, is to face conditions that challenge us to imagine new ways and concepts of seeing. Each new observation that defies our models serves as a signal that could lead us to new physics, offering new explanations for the fundamental workings of the universe. The essence of science lies in its self-correcting nature. Every discovery builds on the last, and each inconsistency or tension pushes us to refine our theories and our understanding of the universe. The scientific investigation of the cosmos remains an ongoing endeavor, driven by the arrival of advanced telescopes, increasingly refined simulations, and a dedicated community of scientists committed to unraveling its mysteries. The universe is not just a frontier, it is the ultimate puzzle. Solving it represents one of humanity's most grand and accelerated challenges. As we embark on this cosmic journey, it is vital to stay curious and engaged with every discovery and insight. We edge closer to appreciating the wonders of the universe. The way forward is sure to be filled with surprises, each offering a glimpse into the profound depths of the cosmos. Every discovery brings us closer to addressing age-old questions like what is the universe, and what is our place within it? Looking ahead, the possibilities in this cosmic journey are endless. The knowledge we have gathered may reveal new stellar events, uncover a deeper understanding of dark matter and energy, and perhaps even show evidence of extraterrestrial life. Technologies will continue to evolve as we explore space and investigate its mysteries.